So, welcome to lecture 15 of MCS 472. In this lecture, we will introduce linear programming. Linear programming is the name for a very important class of optimization problems, and it's often also synonymous almost with the simplex algorithm. So this is a course on computation. The simplex algorithm is one of the important algorithms to solve linear programming problems. So we have a Jupyter notebook waiting. I hope to indicate how one can rather easily formulate and solve linear programming problems. So linear programming is a huge subject, and one lecture definitely does injustice to this very useful and also very beautiful mathematical subject. I will end with some project topics too that start with literature studies. Okay, so let's dive in. What is linear programming? Well, it's a class of optimization problems. Constraint optimization is also the good word. We want to maximize profit or to minimize cost subject to inequality constraints and equality constraints. When we maximize profits, our inequalities are typically formulated as by their upper bounds. When we minimize costs, we typically have lower bounds on the inequalities. So these are the two pure forms of the problems. So what is then the linear programming problem? Well, both the objective and all constraints are linear. So this then becomes a problem that can be solved with linear algebra techniques. So in this lecture, we remain at the geometry, and we're going then into some examples with software. But in the end, everything is numerical analysis. So in some sense, there are very interesting numerical algorithms and numerical issues also associated to solving these problems. Okay, some terminology. So the constraints, the linear constraints, so they are inequalities, and every inequality cuts the plane in half. So what remains is a polyhedron. So here this is sketched in the plane. So we have a bounded polyhedron, and this is an example of a feasible and a well-posed problem. In particular, we say that there is a solution to this problem, and there will be a unique solution, in this case here, when the polyhedron is not empty. Well, I'm sorry, the solution might not be unique, so I misspoke. So we will see cases where feasible and well posed does not necessarily mean that the problem has a unique solution. But feasibility can be translated in the polyhedron not being empty. So the constraints are in agreement in the sense that they are not conflicting. The problem is said to be well posed if the polyhedron is bounded, like is the case here. So our constraints represent half planes, and the intersection of these half planes is a polyhedron. Okay, so we can turn things into a standard form. So we have here the form of a minimization problem, where we have a cost vector, the coefficients c, and we have a system of linear inequalities that we can turn into a system of equalities by adding slack variables. So the extra variables z are extra, and they turn the original inequalities into equalities. Easier to work with. Typically, all our variables are positive. Should we have variables that can also be negative, then we split them in a positive and a negative part. So the minimization problem then becomes in standard form with the slack variables, where we have the equalities, and all the variables are positive or zero. So we're looking for a solution to a huge linear system. Typically, you can have more equations than unknowns, or fewer equations than unknowns. And we're looking for not to find all possible solutions, but we're looking for an optimal solution. So that's one of the standard forms that uses a minimization. One can formulate very similarly with a maximization. Okay, so let's look at an application. So we want to plan a meal. We have it should be healthy, so we have requirements. So here it's also formulated as a minimum. So we need some minimum of every nutritional element. We have some minimum requirements. We want to be economical. That means that for every food quantity, so for every item of food, there is a price. And what we actually want to determine is we want to determine the quantities so that the price is minimized. So the cost of our meal is, so we multiply every quantity with the price, with the unit price. We sum that all up. So the what we want to minimize, is the price, the cost of our meal. But we want to, so ideally it would be zero, but then we wouldn't have anything for the nutritional requirements. So zero is not here a feasible solution if you want to survive. So we have then these constraints that tell for every nutrient how many do we need. So the requirements are the right hand side, so they're now formulated as the C's. And we have for every quantity, for every food group, we have a coefficient in the matrix that's going to determine how much food contributes to satisfying the nutrient requirement. So this is all quite abstract. We will see a concrete example. So you see the Jupyter notebook is waiting. But let me first introduce an exercise. So here we are advising a car maker that has, for very simple reasons, simplicity reasons, three types of vehicles with the profit margins. So if the goal is to maximize profit, then there would only be Cadillacs that are being made. However, Cadillacs are supposedly not very fuel efficient. So we have the requirement that the average car must have a fuel efficiency of at least 18 miles a gallon. So if we would make only Cadillacs, then we would not get there. On the other hand, if we would make only Chevrolets, then we would indeed satisfy, but our profit would be not good. We also have the time requirements. So how if our plants are up and running, how many minutes that it takes to assemble one car. So we have these constraints, these givens, and the constraints. What is now the linear programming model that would need to be solved to maximize the profit? Deciding how in in 1 8 hour day, so you can calculate how many minutes they're in there. In 1 8 hour day, how many cars should be made of each type? Okay, how do we do this now? How do we solve this problem? Well, the idea of the simplex algorithm is actually quite simple. So we have our polyhedron, and they are defined by these half planes. So we think in the plane. So where two lines meet, they intersect in what is called a vertex. So it's an intersection point. Another word for vertex is a corner of our polyhedron. So the idea is we are going to find one vertex point, and sometimes we sometimes that's quite trivial. So um, 0 0 is often a trivial vertex point if it's there, and then the main step, step 3, is to improve the objective value by going to a neighboring vertex point. So the vertex points are connected. We go to a neighboring point with a higher optimal value. Okay, so that's the idea in the abstract. You see, step 3 is the repeat until. The modeling, so bringing it in standard form and finding a feasible point, are separated in 3 steps now. So getting started in the simplex algorithm is often already more than half of the solution. Okay, let's look at the numerical example, which I will solve geometrically. So we want to also here do a plan, a production plan. So we want to decide how to organize the production. We have only 2 items. The first item gives us a profit or can be sold at $3, while the second item gives a larger profit. So we can sell it at $5 per unit. And then the constraints, imagine that they are labor resources. So, for example, you can imagine that while the second item yields a larger profit, it takes more skilled labor to build it. So that could be the constraint why you can only manufacture 6 instead of 8 units for X1. Could also be storage capacity. Okay, so this is our toy example. And since it's in 2 variables, we can easily plot it. So let's look again at the 5 constraints. So we work in the upper quadrant. All the variables are positive. We don't make negative quantities. So, and then we have the rectangle essentially. So x1 is bounded by 8. So we have the 2 vertical lines which describe the constraints, the band for x1. then we have the band for x2. So that would decide that we have a rectangle, but the shape is a little bit more interesting. So we have a slanted line, 3x times x1 plus 4x2 less than or equal to 36. So you see our feasible region is the green zone, defined by these blue lines. And then we have the red dots. They are the intersection points, the vertices. So it's a very important theorem in computational geometry that says that any polyhedron or any polygon can be defined either by its inequalities or by its vertex points. So you can take the convex hull of the points and get the equations for the lines or for the hyperplanes that way. So there is a very beautiful mathematical theory here, which we unfortunately, which could if you are interested, could into computational geometry. So linear programming is also used there. So it also has very important mathematical applications. So the convex hull problem transitions from the vertex description to the to the linear inequality description. Okay, for us it's important. We are the green zone. We have the green zone. We have what we called a well post. So we have a bounded polygon and we have a feasible problem. So our problem is well post and it is feasible. Okay, so that's one part of the data. Then we have the objective function. So we can visualize the objective function as well. So 3 times x1 plus 5 times x2. So if you decide, and we will optimize this problem, then we see that it's actually better to produce units of x2. But we can only have 6. So if we have these coefficients 3 and 5. So if we produce 3 items of x2, then we have a profit of 15. To realize the same profit 15 with x1, we have to make 5 instead of 3. So we have to, so the way to read this objective function is that there is a trade-off between producing x1 and producing x2. So I hope that on the previous slide I had the convex hull problem, and that was kind of mean of me to get you into a difficult mathematical problem. What I'm trying to do with this slide is more appeal to the economical common sense. So I hope that one sees that there is a trade-off. If you want to produce only one of the two and you want to keep the profits the same, then you should stay on the red line. So where the red line actually meets the 2 coordinate axes. So if you want profit 15, you either produce 5 items of x1, so then you are at the horizontal axis, nothing of x2. If you are on the vertical axis, for profit 15, you have to produce 3 items. But there's never any reason why you would stop at 3. So if you have to decide between the two, you will immediately go for 6. So you will immediately go from a 0 to 0, 6, where we have a profit 30. Okay, so that's what we did. So we started with at one corner. So if you do production planning, there is most likely always a feasible solution that's doing nothing. So you're not producing anything. I think that's not really something that economists will like, but here for this model, it is a feasible solution. Okay, so in the first move, we went to from the point 0, 0. So we went following this black arrow here. We went from 0, 0 to 0, 6, going from one vertex to the next. Okay, so we have not produced anything of x1, and you can see that if we move now to the right, we would improve our optimum. So we can no longer increase our production for x2. Perhaps we don't have any more laborers who can make x2, but we have still capacity. We can still raise x1 from 0 to 4. So following the black arrow, we go to 4, 6. Why stop at 4? Well, observe that there you hit another vertex, and that's the vertex that is going to be defined by the constraint 3 times x1, so 3 times 4 is 12, plus 4 times x2, 4 times 6 is 24, 12 plus 24 is 36. So at each vertex we do have an equality. Okay, can we move further? Well, actually, we could certainly not go to the right. And why would we go down? So that point where we are currently is actually the optimal solution. And how can we see this also? So the optimal value is 42, always a very nice outcome of any calculation, although it's not really lengthy here. So we found 42 as the optimal solution. And one way to see this is that the red line that has our objective, that represents our objective function, the red line touches at that optimum. So that's the only point in the feasible region. Now you can see that I misspoke in the beginning about the uniqueness. So now you can see that if you would start to change the 5 into a 4, then you would have an entire line segment of optimal solutions. Because then the objective function would be parallel to one of the constraints. So this is a very simple example, but you can already see, you can already from here try to formulate a condition on the uniqueness of the objective. And you can also see why the optimal value has to happen at the boundaries. So the polyhedron can be quite complex. So here we only had 2 steps in essence. But you could have many. You could have almost like a circle, and but you will still do this in a finitely many steps. Okay. Now, how do you do this in Julia? Well, Julia has the modeling language, the JUMP. So it's a modeling language and a collection of packages. What is used for linear programming is the GNU linear programming kit. So GNU means not Unix. It is distributed under the licenses of the Free Software Foundation. For the first tutorial, we have our diet problem. So our diet problem was rather abstract. Um, there is also a free book already in the second edition, and it's free to read online, and there are plenty of examples. The two project proposals associated with this lecture invite you to also use that, use Julia. So let me switch to the Jupyter notebook. So here is how we start. So we have our diet problem. If this is the first time that you have to do this, then you have to press yes after the question using GUMP. We encountered data frames already in one of the lectures in the second week of classes. I think it was lecture 4, if I'm not mistaken, or lecture 5, one of these two. So we will solve linear problems. So the entire package is quite huge. So also even in the subject of linear programming, you can get lost. But there are some problems that you could focus on. So the diet problem is one of the problems in the production planning. Is our typical problems. Okay, so let's me walk through this. So we have food groups. For every food, there is a coefficient, a cost coefficient. So first of all, what are the dimensions? The dimensions are n for the number of foods that we can choose from. And then we have the nutrients that we care about. So we have m for the nutrients and n for the foods. And we have coefficients. So for every food, so the I is the second index here. For every food, we have a nutrient profile. So how much does this food contribute? Now we have requirements. We have lower bounds and upper bounds. So about of some foods we shouldn't really eat too much. So it's a realistic problem. This is where the data frames comes in as well. So the data frames are going to help us. Okay, we want to determine now what is the problem. We want to satisfy all our requirements, so not eat too little, not eat too much of every food group. We want to determine them so that we minimize the costs. So the cost function, so the objective, is formulated by these n foods multiplied with their cost coefficient. And then we have the constraints. So it's quite flexible here. So we have linear inequalities that are given by lower bounds and upper bounds. So we have the nutrient profile for every food. We multiply this, and that gives us the upper and the lower bound. So then we have our optimization problem that's formulated by the constraints. So also do not forget that everything should be positive. All the variables should be either 0 or positive. So this is a linear programming problem, as everything is linear. So this is another formulation, another definition, if you like, as a minimization. Now, how do we get the data? So here you see the data for, let me widen this a little bit. So we have a data frame. So I copied and pasted this from the documentation, from the tutorial. So this is how it is defined. So we have the foods And we have, for every food, we have a cost in the second column. We have the calories, the protein, the fat, and the sodium. So you can see the fat and the sodium. This is where the upper bounds are going to come from. There is no sugar, so there's no constraint on sugar. Interesting. Okay, so here it looks nicer when everything is formatted. Okay, so we have our 9 foods, and we have four four columns that will be used. So the second column will be used to define our cost function that we want to minimize. Then we have the constraints defined by the nutrient profile. Okay, so let's continue to scroll down here. So we still need more data. We have the bounds on the calories, so it's quite within a band. So we want to have around 2000, so we can give or take 200 calories. There is no limit on the amount of protein, but fat and sodium, they are giving us the maximums. So for every nutrient, we see the requirements. Okay, so we always start by defining a model. So we have to tell that we are solving a linear programming problem for which we use the GLPK, the GNU Linear Programming Kit. We have to define the variables. And here this is kind of nice. So you don't really have to write a loop, although you can enumerate things. But we can pick, we can define our variables from the data in the data frame. Okay, so we have our 9 variables, and then we have the objective function. So you see it's also a modeling language, but very closely following the Julia syntax. So then we get to our constraints, for which we use the nutrient profiles in the foods data frame, and then we also use the limits. So here it gets rather technical, a little bit more technical. So we have the limits that are our constraints. So we have 9 unknowns, so we will have 9 columns. So you can also here see them all with the variables. We have 9 columns in the matrix, and we have 4 constraints. So we will have 4 because we have 4 requirements on the. So here they are. Well, I said we have 4 constraints, but then also we have all the positivity constraints. So we have the 9 extra conditions. And so it's good to print a model. I think that the positivity constraints are kind of automatically. We don't need to specify them. Okay, so far so good. Now comes the solving. Okay, it went well. It solved. We found the objective value. So that is how much our meal will cost. $11.83 if we round up correctly. Okay, what is the meal now? What can we eat? Here is what we can eat. there is it's an interesting solution. It's most likely a solution that was invented, or the model was probably set up by somebody who's a programmer, perhaps not a dietist. We have a lot of dairy, milk and ice cream, not too much meat. Suppose that I want to change now the modification of the problem. So I want to eat some salad. So say one quantity of salad, and then I'm out of luck. I see it's infeasible. So there is no solution. Okay, so you can see that there is some terminology here that cannot yet understood. So there is the dual, which I still need to explain. So in the case when there was a solution, there was the dual was equal. So minimizing cost is the same as maximizing profit in economic terms. That's what duality is. Why is duality important? It actually gives a certificate that your constraints are conflicting. So they are making the polyhedron having an empty solution. So here we are working in a 9-dimensional space, so it's kind of difficult to visualize this. Okay, very well. So we are done with our Jupyter notebook. So let me go back to the slides. I still have to explain duality, so we still have about 14 minutes left. So what is duality? So this is phrased in the abstract. Algebraically, you could see that we are flipping the constraints. The constraints become the cost coefficients, and the cost coefficients become the right-hand sides. So we can give this an economic interpretation. So we have the primal variables. So if we are doing production, planning a production, maximizing the profit, then the dual variables are indicating the contribution to profit for every unit that we are using. So the constraints are the amount that is available for the resource. So algebraically, it is a transpose operation. Let's look at our numerical example. So we, instead of having 5 constraints in 2 variables, we are going to have also 5 constraints, but now in 3 variables. So sometimes it's one formulation might sometimes be advantageous to the other, although many algorithms are working in a primal dual way. Once one has solved the dual problem, the primal problem, one also has the dual problem. Okay, so for our diet problem, so we looked at the diet problem. So what is the dual of the example? And what are the units of the dual variables? So the units of the primal variables were how much of each food group. These are then quantities. What are the units that you're going to use of the dual variables? How can you interpret the dual problem in this case here? Okay, here is another modeling problem in the investment. So you have some money to invest. So some types of investment are more worthwhile than others. Um, but you also have constraints. It could be that the constraints um, are that that some shares are more risky, so you're not allowed to put everything in type C. So only 20% of your total portfolio can be spent on C. And you should at least spend $10,000 on type A. So formulate the problem, bring it into a form that you can solve it with Julia. Okay, so that concludes the first part of, or the first two parts of the linear programming. So now in the remainder, I will not need the entire 10 minutes allotted for this lecture. So let's look at two topics for a second project. It starts with a literature study, and I was using the search function in our UIC library. So this historical paper is quite interesting because it lists three industrial applications. So this paper is available also to you. The purposes of this paper, of this project, is that you select one of the problems and you formulate it in your own words. So the numerical data you may have to either look up from elsewhere or come up with an instance that is feasible. And then solve the instances. So the dimensions that are reported there are 50 and 100, I remember, in one problem. And for the time, we are talking the 1960s, so this was quite intensive. So there are time units listed there. But it should be apparent that what were actually difficult but realistic problems for computers are now actually quite straightforward exercises with our current technology. So the two project proposals invite you to explore a little bit also the computational side of it. So the second problem also starts with a literature study. So there is the book I could download, I could read the online version via our library. So read the beginning of the book. Actually, read the entire first chapter, which is not that long. At the end, we have encountered Fourier already multiple times, and we are going to encounter him again at the end of this week. It turned out that Fourier was already familiar with the study of linear inequalities. The linear programming goes back to the 50s to Danzig, um, and there are also other people who should be named. So that's also an important um, to read this reference. What is required of this project? Describe the managing of a production facility. In a way, we have solved this problem already. Our first numerical example was with 2 units. But here, set up a problem that can actually scale for any dimensions. So you have any number of units, any number of resources that are constrained. So in this project, you will set up a general program Try also to come up with to generate data that lead to a feasible problem. So and solve the instances. See how long it takes. So if you work with hundreds of dimensions or even thousands, so the question is here, how far can you push it? Is this a problem from if you took an algorithms course? What is the complexity actually, the computational complexity of this production facility? Is it linear? Most likely not linear in the dimensions because you have to solve linear systems. So also the complexity of these polyhedra, so they can be quite daunting. So can we actually? And the answer is, of course, yes. You can solve problems that have hundreds, thousand, 100,000 of dimensions. So the make a computational study of this, and so it is a polynomial time on average on random problems. That's actually the conclusion of this project. So both projects are very similar. Um, Although the second project is more geared towards computational costs in general. Okay, I hope this was interesting. I hope if you have never uh, encountered linear programming, that this was useful. At the same time, if you have already heard the term, I hope that you can also kind of appreciate the mathematical beauty of it, and especially also for this course, the necessity for industrial applications.